Hi guys, I'm Matthew Feigal from, originally from America, but from the Amsterdam Google office. And my role is Cloud Platform Solutions Engineer, which basically means I help customers understand what our cloud platform hosting products are, how to use them, figure out any barriers they're having, and make sure life goes smoothly and they're happy. I do a little bit of sort of DevRel and speaking stuff too, because a lot of times the community doesn't really know our offering. So I'll take chances like this to chat with the community about what we have. So thanks to Startup Wise Guys and to DevClub for hosting me here tonight. I'm really excited. One of the things I could talk about a wide range of how people run stuff on Google, from like running bare bones, well not bare bones, virtual machine instances, to running platform as a service where they have a little sandbox where you deploy your code and we take care of everything between. And the sort of whole range, smooth range, hopefully not bumpy range of moving up and down in that continuum. But I think you guys just had a talk about Docker last month. So it felt really good to come in and focus on a very specific spot in that range where you're using Docker and what happens when you have, congratulations, Dockerized your app, but now you realize you have 6 or 7 or 10 different types of Docker processes running, and you need to actually, Docker's running, and you need to actually manage them well. So first I'm going to rush through briefly what containers are, because you guys saw it last month. Is this working? No, maybe not. Okay. Or maybe just the click button. So I'm going to rush through the story of Docker. Who was at the Docker meeting last month? Pretty good. Okay. Who wasn't here but has a good idea what Docker is or containers are? Okay, good. Then I can rush through a little bit. The old way was you had a shared machine. You and your other developers deployed stuff on the same machine. You overrode each other DLLs. It was really chaotic. There was really no automation. It was a headache. You couldn't efficiently use those machines. 10 years ago, still doesn't work. 10 years ago or so, we started doing these virtual machines, which seemed like the salvation. Oh, I can have my machine packaged so my libraries don't overwrite everybody else. But there was still a lot of overhead. You were running a guest OS that was taking up a lot of space. It was still kind of slow to start them up. And a while ago in the Linux community, we started to be able to do containers, which meant you're running on a host application, a lot of benefits here. You maintain one kernel, and you package up your application and its dependencies in a really tightly coupled little package. It's almost like a sealed binary almost, right? That just has everything your piece needs to run, which is exciting. Yay! The big thing is they provide isolation from each other, so they don't overwrite each other's data. They also provide isolation in terms of resources. So you can say this one should have half a CPU and this much memory. And so you also can kind of control your quality of be very predictable about your performance that way. There's no noisy neighbor problems. I'm not going to go into details. Google is a big fan of containers because we've been using container technology, not Docker. It's a little important to separate Docker from the container concept. We've been using container technology internally for 10 years. We are really big fans of it, and we feel this is the way we've been able to run our business successfully and grow it. Everything at Google runs in container. I'm talking Gmail, all the services that make up Gmail, that make up web search, that make up maps. We run MapReduce projects, so we're running like basically Hadoop type stuff in containers, batch jobs. The Google our file system is running in containers. That's pretty advanced. I don't think Docker doesn't quite do that today, and I wouldn't recommend it. But that's what we use it for, like all sorts of these sorts of things. Even who's running Compute Engine? Who's logged into the cloud platform environment and started a Compute Engine instance? Okay, a few people. Those are virtual machines running inside a container. So So we're running a container and offering you fully, the virtual machine that you've been promised. You said, I want 8 cores and 32 gigabytes of RAM or whatever. We're protecting the resources for that because it's running in a container. We know we can promise you that resource. We launch over 2 billion containers a week. So when you're doing that, and you're trying to schedule those containers across a cluster of actual physical machines, you run into a bunch of challenges. Oh, sorry. There's all the reasons that containers are awesome. What we're really excited about is that if you look at the Google trends just over the last year or so, Google, Docker is becoming a dominant force in container technology. It is an implementation of the container idea. There's others. And we're really excited that the world is adopting them, because this is how we kind of feel that you need to run large-scale computing. So it lets us kind of bring the way we do things closer to you guys and let you guys do stuff kind of the way Google does. Since we're a little short on time, I'm just gonna rush through. Not rush. I'm gonna skip. Okay. I don't know what any of this slide means anyway. No. No.
The content is important.
Yeah. Okay. There's these principles behind Docker, which is that the apps, or even the components of your apps, should have a defined service level objective. We don't talk about service level agreements, we talk about objectives. So service level objectives like this one should be able to return results this fast and should be able to process this fast. And you can you can reach that because you're in control of what the container, the resources the container has. And so if you run the same application in one container or another container in the same infrastructure, they should give you approximately equal results. So you have a lot of control over actual performance, as well as the DLL, as well as all of the kind of benefits you get as a developer of being able to just package up an application, run it on your laptop and know it's running, send it to your managed hosting and know it's running, send it to Google and know it's running, which is great. But you also you can have really reliable performance. I mean, there's a lot of other benefits for running Docker in general. But now, generally, you're not going to just start a single virtual machine and put a matching fully sized container on it. Once you start thinking about your application in Docker perspective, you probably don't want to have one Docker container for your whole application. So it's not like you have my PHP instance and my SQL server in the same Docker container, because that's one is your data store layer that might need to scale or behave in a certain way, might need a certain set of resources, and one is your web front end, and maybe one is your API, maybe one is your static files, and one is your. And these things have very different properties. They need to scale differently. They need to respond differently. So you start breaking your application into smaller and smaller components in Docker. Now you need to figure out, this is just one of the challenges that we bumped into, is when you have this isolation, how do you schedule them across machines? And scheduling, so you say, okay, say you've got a 4-core machine, pretty small these days, with 8 gig of RAM. Okay, let's put a small Docker container here. It's sort of reserving this much space. Let's put a large Docker container here. It's reserving this much space. And then let's put a really tiny Docker container here. It's using that much space. That much CPU and memory. And so we're out of memory. No, we're out of CPU cores to give away. But obviously you can see a small problem here. It's a percentage-wise problem. Maybe for one application, it's not a problem. But if you're running 10,000 cores, you're losing 12.5% of your capacity right there, because you've lost that 1 gigabyte of memory, which you can't use now because you have no CPU left over to use it. And what you end up here with is, this is just 2 dimensions, the cores and the memory, but it's really a multi-dimensional problem. I've kind of flattened it down to 2 dimensions here, but there's also network access and disk access, and quite a few other capabilities. So it's a multidimensional problem of how to pack these things in efficiently and run efficiently that we've worked on really hard to get right. What are some of the other benefits of strong isolation? Yeah, you don't have, it's predictable, it's predictable, but it comes at maybe the expense of losing some of this performance resources. The negatives are like I showed you, you can strand stuff. It's also a little confusing. People don't know how big does this Docker container need to be to run. So they might, I've cut a couple slides out, but they might make a Docker container that's this big when their application actually only really needs this much, but they didn't really know in advance how much they needed. So they might over-provision or under-provision the resources for their container. So you need to have smart auto-scaling that lets people scale it down a little bit, and the Docker image or the resources that Docker image will change, or you scale horizontally by adding new Docker containers to it. And then there's even more to the story. Like if you're just doing this on your own, it's not just about the Docker images that you're running, but the kernel itself is on that machine, and it's using resources. And we can guess what it's going to use, and we're pretty good at guessing what it uses because we run a lot of kernels, and you guys do too. You're pretty sure how much kernel, what's going to be needed by the kernel, but you're not quite sure. So your guest machine, your host machine has actually an operating system running on it, which isn't really reported as part of this Docker container, and it could go up and down a little bit. And suddenly you've overcommitted and bumped this machine. This Docker gets destroyed and needs to get restarted somewhere. Best case, this Docker gets killed and needs to run somewhere else. Worst case is it gets killed and it doesn't get restarted somewhere else, and then your service is missing an important component. So that's one of the lessons that we have to solve when we're solving this how to run containers at scale problem. Oh. Since I jumped in really fast, I forgot to give you a roadmap of where I'm going with this story. Let me do that now before I spend any more time talking about how difficult it is to run containers in scale. The first part of the story was Docker. Why Docker is interesting, what the properties of it are. Past that already. The second part of the story is Google has put a lot of energy into figuring out how to run lots of Dockers together at scale. The third part of the story is we've released this open source tool, Kubernetes, which is not an exact copy of what we do, but it's sort of the founding principles behind how we do it. We've opened it off as open source. So I'm going to go into actually quite a bit of detail about what the components of a Kubernetes cluster look like and why they operate the way they do. The last part of the story is I have a demo, specific code samples. We're going to start up a Kubernetes cluster that a customer of mine uses for semi-production workloads, and show you the details of how the concept of Kubernetes applies to this. And then if I have a little bit more time, I'll talk about some other cool Docker stuff, but I think I will be out of time. I hope that helps. I'm really sorry I forgot to give that roadmap at the beginning, and now you know where I'm going with this story rather than just going through slides. So other challenges in this space, you might have a system daemon, like actually the agent that's busy scheduling the clusters that can also take up space, or a logging, a FluentD logging cluster daemon, something like that running on the environment. That's also taking up space, and that's also adding a little bit of overhead. This is more predictable, at least. You can predict what this is. I mean, this can fluctuate more easily. This you can predict what it is, or if you can't predict it, at least you can limit it. So we're running these also in a container. So if we've got a system, we're running a container, and we're putting our logging functions in a container, and that way we can control, limit them and control them. The failure modes are not awesome. Like if for some reason something goes wrong, you would probably decide, okay, this is the first thing that's going to get destroyed, and then you might, I don't know, what do? Shut down your logging? Or I mean, it's not a great solution, but it's the solution we have in place usually today. Another challenge in this situation is if anyone is uncontained, so if anything is running on the system that's not in a container or that's not predictable, it could eat up all of the space and steal space away from your Docker images. So you have to be very careful about that. If you're working with developers that you don't have full control over, they put out a Docker instance that they haven't specified the CPU or memory. I think the current Docker implementation means that it gets as much as it tries to use, which means it just ate up all your extra space that you thought your other Dockers had, which isn't great. The way we do that internally at Google is if you don't specify the constraints for it, you get the leftovers. As opposed to being greedy, you only get the leftovers. You don't only get things that aren't claimed on that system by other things, and you're going to be the first one who loses resources. I don't think Docker does that today, but the container community is continually learning lessons and growing. So, yeah, let's just skip over this. So, container isolation today doesn't deal with these things. Container isolation is a really nice way to package it up and deploy it, but it doesn't handle all of these questions that we just went over about what happens when you're running lots of containers and scheduling them and trying to figure out where to run them. It's pretty much voluntary, so people can screw it up. Somebody could install something else so it's clearly an area that's going to improve, and that's where we get to. And there's more things. So this was just the isolation question, and there's more questions in this whole space, like where should I run my job so that it has optimal connection to the other services it needs? Where is it running right now? Like how do I reach other? How do I do service discovery? Right. So I've got I've got a Mongo database cluster. How does my web Docker know where to find it? What makes up a single unit of service, right? So I've got a service. Everybody's talking about microservices these days. What makes up a single unit of service? Is it maybe the service unit is the web front end and the data storage is the service that we need to talk to? So authorization, how can we connect to it? How's it going? What's the behavior and the performance like? And now we get to part 3 of the story, which is Kubernetes, which is a wonderful name that everyone is really excited and understands right at the beginning, right? Maybe not. It comes from the Greek, and the root for the word governor. It's also the root for the word cybernetics, kind of interesting. We have the system that we use internally we call Borg, but we're not allowed to officially use that. Oh, this is being recorded. I didn't say. No, I mean everyone knows it is, but we're not allowed to call it that because it's owned by a wonderful science fiction franchise that would get mad at us, and we don't want to piss them off because they have phasers. And so, the idea behind Docker was to show the world how we treat application management as managing applications and services rather than managing the machines themselves. If you're these days, well, today many people are working around with base computer, virtual machines. But I really think in 3-4 years, it's going to be very rare that you're spinning up an instance and installing something on it, because then you're dealing with really tiny little stuff that's barely repeatable or hard to manage. We treat our whole data centers as one computer and just schedule jobs over it. And Kubernetes is a way that you guys can treat your units of computing in a similar way. So it runs Docker containers. It also, I believe, it supports the other container technologies that are coming out, Rocket, and I think there was another one I've heard about recently. One really important thing for us is that it supports multiple clouds and bare metal environments. So this isn't Google's play to say, come use this cool thing, but it only works on us. It's Google's play to say, we believe this is the right way to run these type of workloads. We want the feedback from the community, so we don't want to just put out something from Google. It's open source, so it's being contributed to by Microsoft, by OpenStack, by a whole bunch of partners, and by just a bunch of people like you guys who are excitedly experimenting with it, finding the rough edges in a pre-1.0 open source project, and either giving feedback or making pull requests yourself. So while it's inspired by us, it's really getting a lot of input from the community. And this thing about multiple cloud and also supporting bare metals, you can run it on your laptop, you can run it on your own on-premise center. We believe in workload portability. We believe that you should be able to create that cluster and run it on-premise, and you should also be able to run it on us. Now, commercially, that's a long-term play for us because we think you set up this cluster on yourself, you're happy with the way it works. Hey, let's try running the same scripts over on these guys. Well, that works really well. Let's try it on those guys. Oh, it doesn't work as well. Let's pick these guys. And we're hoping, we believe, that will be us in the long term. So in other words, it's not entirely altruistic. We want you to try it on premise, and we hope that you'll eventually try it on us and really love it. Some of the principles behind it. One should be declarative. So it should be that you define the system state as you want it, rather than sending commands. You say, this needs 4 machines or 4 pods, or we need a load balancer like this, rather than giving a command like add a new pod, add a new worker node. Because that's too easy for it to get out of control and for your vision of reality to miss reality. You define reality in the Kubernetes declarations, and then Kubernetes makes sure that that's what the case is. And I'll go into some more details about that. Control loops, so there's continuous control loops, observing the state, fixing the state if it doesn't match, and then continuing to observe and rectify. We want to be simple rather than complex. So there's so many things you could try to do in this space, and we're trying to keep it simple. At least at the beginning, we want it to be really easy. We don't want you to have to change your existing applications. It should be compatible with your legacy applications as long as you can Dockerize them. Because asking you to change all your legacy applications just to use this is a recipe for failure of this project. So one of the simple versus complex examples is today Kubernetes really supports like up to 100 machines. Is what its goal is for the 1.0 launch. Not that you couldn't use it to run 1,000 machines and stuff like that, but we have chosen to focus on the 99% of the workloads that customers are going to want to run with it, which is smaller groups of machines, up to 100 machines. Focus, get that working right, and then once that's done, go up from there. So I'm going to just go into the actual detail slides. Are you guys familiar with the pets versus cattle concept for running virtual machines and automation and stuff like that? A few? Okay. Very briefly, virtual machine instances, there's pets, like you take care of it, you feed it every day, you take it to the doctor when it's sick, and there's cattle. There's hundreds of them. They just have a number rather than a name. If one gets sick, you give it a shot of antibiotics and hope it works. And if it's not, sorry, you get rid of it and get another cow. This is really the kind of the modern model of automated environments. It's not just a Kubernetes thing. It's really, if you're doing anything with an automated environment, you do not want to have pets in that environment. You don't want to have one instance that you really have to tinker with and take care of, because the very best case is someday you're going to get sick and nobody's going to be there to take care of it, and then it's going to crash. You want everything, you want these things to be automated. You want the scripts to take care of them. That's the pets versus cattle mentality. That's a founding design principle of Google. High-level design doesn't quite fit in my story flow, but I'll do it anyway. High-level design is you are talking to Kubernetes over the command line interface or the APIs or a user interface. Kubernetes is running as a master node here. So Kubernetes is figuring out where to schedule all of your jobs. And so you make changes. Say if you need to change something, you say tell it to make the change. Okay, we're going to increase this. We're going to put an autoscaler in here. The master is what's doing, keeping an eye on things, checking the state, and scheduling new jobs out on kubelets, out on your little nodes. How am I doing for time? 30 minutes left? Am I putting anyone to sleep yet? Hopefully not. Primary concepts behind this are a container, well, you know that, the package, the Docker. A pod is a group of containers that are co-located and shifted around. It might, these days most pods I see are just pods with a single container in them. This is my front-end web server. But it might be that you have a couple containers that really need to be close to each other. They need to be on the same machine. They're really providing critical services next to each other. You might put those in the same pod. But most examples I see out there today just have one container, one pod. The controller is this continuing observation loop of Kubernetes that makes sure that what's running out there in your environment matches what you've defined. The service is where it starts to get interesting. The service is how your pods find each other. So your front-end web server pod needs to know where its back-end, where it's actually, the outside world needs to know where your front-end web service is. So you define your front-end pods behind a service. Load balances are created. Scaling can happen automatically there. But the outside users just find your front-end web service and get in the door. Your front-end web service needs to know where its logging function is or where its data storage function is. Those are defined as services. Kubernetes can throw them around anywhere in the environment, but they will always be found through the service name. Actually, labels. And labels are the way you define the pods and actually all the resources in Kubernetes. So the controller is always doing these queries for give me the resources with this label, and then it finds out what the labels are. Because we found that before we had labels, everybody would name their machines. Everyone was stuffing metadata into their machine names. So you'd have like 250 character machine names like Mongo server, production, version 8, API what, and then they would, if they needed to define that machine, they would parse out these machine names. It was just, we were twisting ourselves crazy trying to put metadata on machines that way. So pods, here we go. Actually this is, okay, so here we have a good example of a multiple container pod. The pod really is, like I said, the containers that really need to be really connected to each other. They should be physically located close together. They shouldn't be created or one of them shouldn't be created or destroyed without creating or destroying the others. And this is an example where you have a web server that's handling your front-end web server that's handling your web requests. You've got a little local file volume where it's getting static content from, and you've got a separate container that's checking for updates and making sure that this data is updated. This is a really good example of a pod with multiple pieces. If this died or this died or this died, the whole system would be kind of worthless. But so together, this is your scalable unit that might be replicated several times in your environment. They're going to run on the same machine. I'm going to skip networking. It's a bit too much detail. That picture is not quite correct. Why is that picture there? There is no network address translation. So I'm not quite sure. Now that I look at this picture more closely, I don't know why it's there. I think it's to describe the different pods and nodes will talk to each other over through services. Kubernetes is going to tell them the IP addresses and the port numbers. You're not going to do network address translation. You're going to be able to talk straight between them. So when this makes a call to this one always sees the correct address as the refer. Now that I'm looking closer at this picture, I'm really confused. Let's move on from that because, frankly, this is internal design principles of Kubernetes that they work. I think this is the more interesting part. So the pods reach each other. Oh, maybe this is the story of what happens when you. Oh, okay, now I get it. This isn't the Kubernetes story. Sorry. This is the story of what happens if you're trying to do Docker networking on machines that you're running yourself. So you've got 3 different machines with 4 different Docker instances running on them, and you're trying to get them to talk to each other, and it quickly becomes a real pain in the ass. Have people experienced this with Docker before? Yes? Okay. Let's edit that part of the tape where I didn't know what I was talking about.
Over there.
Yeah, I know. I was too focused on why the hell are we talking about NAT here to read the title. So in Kubernetes, the pods are able to talk to each other. There's no NAT address routing, and they can be running on different physical nodes. And Kubernetes is responsible for making sure that they all know where each other are. And this is, like, as it says in bold at the bottom, this is a fundamental requirement. So sometimes when people try to set up Kubernetes on their own specific environment, they will find that the pods can't talk to each other. And that's because there's some stuff happening where in their environment they don't have the routing set up correctly. If you're running Kubernetes in a Google Compute Engine environment, or pretty much any really bare bones, simple networking space at home, they will be able to talk to each other and find each other. It's when you get into more complicated, when you have a network with much more complicated routing rules that you might run into trouble, then go read the documentation and figure out how to fix it. Yeah. So does that picture look better for finding your IP addresses and talking to each other? But then once you have this and pods start being moved around, that pod moves somewhere else, the other pods need to know its new IP address, but we'll get to that in a few slides, how that happens. Labels can be any metadata. You attach them to any object, and they're really the identity, but also like the metadata of the objects. And it's the only way we use to group things. So you really want to think through your labels. So in this example, we have all of these are labeled with the same application name, but you can write some queries. So if you want to say, give me all of the pods that are serving Nifty, the application, great. If you say, give me all of the front-end pods. So you write a query, and you get all of the front-end pods. Okay, so those are my front ends. And that's my production, my dev, and my test front end. Good. Give me all of the back-end pods. So here's my dev and my test back end. All right, give me just my just my dev environment. And I receive that. And these selectors are also what Kubernetes is using to check the health of your system and make sure that the correct Docker, the correct pods are always running properly. So replication controllers, for instance, this is what's checking to make sure that your application is running. So it just does a selector for app Nifty. There should be 4 replicas. Oh, there's 3? Okay, the controller is going to start one more. Okay, are there 4? Good, we're happy. If you have, for instance, these 4 nodes running, and one of them crashes, say the network card is flaky, the network card dies, maybe the whole machine's actually still running okay, but for whatever reason, Kubernetes can't find it. Kubernetes is going to say, oh, we've only got 3. It's going to automatically create another pod on another server, on another node that has space for it, hopefully. And then maybe suddenly that network card finishes flapping and it comes back to life. Kubernetes can find that pod again. Oh, right, we've got 5 now. We've got too many, we're using too many resources. Let's just get rid of that one and we're back down to the 4, the state that you defined it as. Services work with selectors also, like we talked about. They create a virtual IP for the other services to talk to it. And I'm not sure what to say about this. Is this clear? Is this picture clear? Like this is how any client, whether it's another Docker image or somebody from outside, will find your service. When we get into the code samples, I'll actually just dive in and show you, here's how you define the service. And I'll dive in and show you, here's how your Docker container registers, like where do I find that service? What do I do that? I don't think I have a lot to say about this slide. It sort of matches what I've explained already. Are there a glaring question about what services are or why they're interesting? Basically, it means that these nodes, well, maybe, okay, you're getting basically a load balancer in front of all of your services. So the client, whatever is asking for it, just talks to the service, which acts as a load balancer, and sends the request through to the right place. So your client only needs to know about the service IP address, and then it's going to get routed through to whichever one of the clients is necessary.
The proxy.
The kube proxy.
Nginx or Nginx or
So
how does it work?
this, I think.
Or just round robin, or how to make your application like
Yeah.
to have like a persistent connection or round robin connection.
So I have to go into territory where I say I think, which I don't like doing, but I think that that the proxy is going to depend on the implementation, your implementation. So if you go to the open source Kubernetes community, there's implementations for bare metal. There's implementations for running on Compute Engine. There's implementations for running on Azure, and every provider could choose to implement it slightly differently. So you'd have to actually go into the code on the open source to see, like, if I'm running this on premise, what is it using? And there, again, I'm going into I think territory because I haven't actually examined my own. We'll look at the control panel on mine and see if we can figure it out when we start it. But so this is where individual sort of implementers might show themselves, like make competitive advantage to say, well, we're going to implement this better than somebody else does. So I think when you're using the load balancer on Compute Engine, it's using Google's internal load balancing tools rather than that we use to handle load balancing for any Compute Engine resource, which we think is pretty good. Man, I hate it when they record me saying stuff I think and not sure about. But I can't answer it today, but I think you could probably figure it out by looking into the open source definitions. So.
Is it possible to use physical load balancer instead of this one?
I mean, I guess you would probably have to, unless you were setting up a HA proxy sort of thing if you're running on premise. Again, I don't know. I guess Kubernetes would need to know about the physical load balancer. And if you could define it, you'd have to define it somehow in your Kubernetes definition that I have a load balancer at this IP address. I don't suspect that it's possible today, but it's a good one to look into the open source details around the kube proxy. Yeah. Okay, so now on to the the demo time. So I'm going to walk you guys through. This is a demo of. It's not a non-trivial app, but it's not a super complicated application. I've got a partner in the Netherlands called Q42. They're an awesome engineering company. It's basically like 50 people that just they love doing cool technology stuff. They hate it anytime they have to do maintenance tasks, because then they're not building exciting new stuff for their customers. So they love App Engine. They love Google App Engine, for instance, because they can just write code and deploy it and not monitor it. But sometimes they want to do something that App Engine doesn't let them do, and then they have to sort of fall down the chain from platform as a service towards infrastructure as a service, and then they get really pissed off at me because they want to stay up at this rapid deployment of unmaintained stuff. So they see one of the things one of the tools they're really excited about lately is something called Meteor, which is kind of an extension of Node.js. So it's built on top of Node.js. And it's you build your code and your backend together in JavaScript. It's actually really neat because it has Mongo database as a backend, and it automatically syncs both your code changes and any changes in the Mongo database automatically between clients, many clients, so you can easily make sort of multi-user environments where people are talking to the same data set and automatically getting updates. They love it for fast prototyping. They sit down with a customer, 4 hours later, they've got a prototype, but they're not confident that the deployment options that Meteor gives scale. You just run a command line, Meteor deploys something, and then it deploys to some Meteor cloud, and they don't really know what it is, and they don't think it's going to scale. So it says, can we deploy Meteor? What would it look like if we deployed Meteor on Kubernetes? And actually, they used Container Engine, which is the Google hosted version of Kubernetes. So every couple of days or whatever, we get the latest stable version of Kubernetes and put it in Google. And so it's Kubernetes running on us, where we manage the Kubernetes master. It's just one less thing for you to worry about. So this is what they set out to do, and we worked on this and had a lot of fun putting it together. So the steps to do this demo, which you can do yourself, is you first install the gcloud command line tools, because that's just command line tools to run commands against Google Cloud Platform's SDK. You also have to update them because Kubernetes Container Engine is in alpha. So it's in alpha right now. So you have to update you have to enable basically the alpha commands to this. You start with a Docker image. So they have a very simple Docker image. This is a private Docker repository. They've created a Meteor Docker image to run. You define what your host name is, and this is I don't know if this is a Docker problem or a Meteor problem. I think it's a Docker problem. This is the one place where you have to set a variable, outside of thing. You need to tell it what your host name is. This we've done already. We've kind of built the Docker image, pushed the Docker image up to the repository. So the Docker image is already built, but I can show you the Docker file if you want to take a look at it. Actually, I should share this link to you. And if you ever want to check this out, it's all on Q42's GitHub repository. And then we just run setup, which I'll... How about I run the setup? Because, of course, these things take a little while, and then we will poke around in the code a little bit. And while we're waiting for the setup, I will walk through diagrams of what we're building very specifically. So I have a nice little setup.sh file. Very exciting. I'm going to run it, but don't worry, we'll come back and look at it later. It's running. Okay. It's going to be a little bit boring to watch that in progress, so let me walk you through a little bit of what it's doing. First of all, we're creating a cluster. So we're saying that the alpha is just the command that says, hey, This is not a production service yet. When it goes to production, all you'd have to do in your scripts is just eliminate the alpha and everything keeps working. Container, okay, we're using container engine. This is the command that says run this command against container engine. Create a cluster and name that cluster Meteor. So what happened right there is we've set up, I think by default, a 4-node cluster. So it's got 4 virtual machines of a kind of a default size. Of course, we could specify more details if we wanted. We set up a 4-node cluster. Then we need to set up our MongoDB cluster. This is, I think, one of the rougher patches in Kubernetes and containers in general is how do you deal with databases and data storage in containers. So I'd love to have debate or questions about this as we go on. What we're doing here is we're just creating a persistent disk. So this is not really container engine stuff. We're creating a persistent disk on Compute Engine and calling it. We're creating a persistent disk. We're formatting that persistent disk. It's a bit of a pain in the butt. It just takes a couple of commands, but we just put it in here. And then we create our first pod for Mongo, and we create our first service. We can look at the commands for those. You can kind of see the definition. So the pod has a little bit of stuff in here, but you're giving it the ID pod. You are setting labels for it. You're telling it, okay, this gets 1 CPU. Yeah, name and image. So this would be your selectors. But you're also mounting a disk to it. So we're mounting a disk. We say this is the name of the disk. It's going to mount it to the container so that our Mongo database is now running and, I guess we're mounting the disk here. The Mongo database is now running and has a mounted persistent disk. The one interesting thing about this is the persistent disk is where your data is being written to. So the persistent disk is not really inside your Kubernetes cluster. Your persistent disk is one of the features, is a resource on your Compute Engine instance. Oh, I'm running out of time. Sorry. If you were doing this at home, you'd probably have to do it on a network file system or something. The reason you have it separate is if this pod gets destroyed or moved somewhere else, you don't want that disk to get destroyed with it because you just lost all your Mongo data. So the disk stays, the pod would get recreated somewhere else, and your disk, and it would reattach, and you would have your disk still. Yeah.
Why you formatted disk? Why did you format disk in advance?
Because Kubernetes won't do it for us. Yeah. The question is, why did we format the disk in advance?
Yeah. Kubernetes can format for you.
Oh, okay. Maybe when we were building this 3 months ago, it couldn't. But it's an open source project that moves fast, so maybe it can now.
2 weeks ago, it managed to.
Okay, good. Okay, thanks. Yeah.
If we are running on bare metal,
Yeah.
how this disk will be reattached? Sorry.
Probably would you use a network file system or?
Oh, okay. So
Yeah. Yeah, because if it is on bare metal, then it's attached to that one machine, which is going to be tricky. Yeah. We also set up the service, and you'll notice that the service uses a selector. And then the service tells us a port. So anybody who wants to talk to this is going to talk to the service. I'm going to move a little bit faster now. Sorry about that. Once the Mongo database is ready, we create the Meteor controller. So we say, okay, set up the Meteor controller, which is what checks and makes sure that we have enough Meteor pods running. We set up the service. We also set up firewall rules. These firewall rules are using Compute Engine's firewall to let. Yeah, that's true. We're using Compute Engine's firewalls because we're running in the Google Compute Engine environment, which has a private network. So we actually have to let outside traffic in to get to our Kubernetes cluster. Otherwise, no outside users can reach it. Quick look at the Meteor controller. Similarly, we set the CPU and the memory. we set, I think we're setting that to use we've got 2 instances of Meteor running, and let's see if it's done. So it's running. If we wanted to examine, actually let's just show if we wanted to examine what was running, if we wanted to examine the pods, do I need to zoom in a little bit here? We can actually examine the pods. You can actually see the labels of the pods. We can see that there are two Meteor pods running. There's just 1 Meteor pod running. It's hard to read this. Let's see if I can. We're missing data. Oh, that's get pods. So we can actually examine the services running. So we've got Mongo running. We have. This is really hard to read when it's overlapping like this. I'm going to be really mean to you guys and shrink it down. Okay, well, at least they're all running. Let's go to the IP address and just see if the service is running. And actually, you guys can all go to this IP address too. Let's see if you can connect to it. Okay, so basically we have a Mongo database in the back. So the IP address right now is 104.155.46.90. And it's a really simple application. Anytime somebody connects, it just throws that into the Mongo database. It synchronizes it all to all the other Meteor clients. And somebody connected and then disconnected. And I mean, Meteor is pretty cool for this sort of instant communication stuff. But what's more interesting is now we're running Meteor on Google Container Engine, and the health checks will take care of it, keep it alive as necessary. If one of those pods dies, we would automatically bring it back to life. If we needed, we could hook up an autoscaler. We can add other containers to do other services, like something more meaningful than show dots. Let me just kind of walk through very briefly what happened in there, just so you get the mapping of. So we have a master which is running, which is actually in this case hosted by Google. We created 3 nodes. Mongo said, give me 1 Mongo pod. So we created 1 Mongo pod. We said, create a Mongo service so everyone knows where to find it. Now all of these nodes would know where to find Mongo. Now give me a web pod and replicate it 3 times. So it gets scheduled across these nodes. And now create a load balancer for those pods. So external traffic is coming in. It's hitting any of these 3 web pods, doesn't matter which. We could also then, there's plans in Kubernetes and ways in Kubernetes to do auto scaling as well. Let's skip that one. I told you I would show you how does Meteor know where to find the Mongo database? Very briefly, if I go into the Docker file, you can see they started from the base Node.js file. We had some run commands like get the application code when we create the Docker file. And we defined some environment variables. So we defined a Mongo URL with the environment variables to go to Mongo service host and Mongo service port. So Kubernetes makes these Mongo service host and Mongo service port available to my application. So we just anytime Meteor or Node.js asks for where do I find my Mongo host or where do I find my Mongo service port, it gets it. And that's just defined by, and you could see that we defined that in the Mongo service and the Mongo port. Really simple there. I'm out of time. How much time would you like me to spend on questions, or are there like glaring crazy things that I haven't talked about that you really wish I did, or things that don't make any damn sense that you want to know about?
Let's take 5 minutes first. 5 minutes.
Yeah, for questions.
Yes.
Okay, so 5 minutes for questions or things that don't make any sense. That yeah.
What are your plans with this?
So it's open source now, even though we're the maintainer. So the plans for Kubernetes is we want people like you to try it out to find the rough edges, because there are rough edges. It's not 1.0. There's a roadmap that you can find on, actually, you want to know the plans? We're very, very clear about our plans. On the GitHub site is the Kubernetes Roadmap. This is more of a technical roadmap of what's going to be developed. Our plans for Google is, we're hosting Kubernetes. We give you a hosted version of Kubernetes if you want to use it. So it's sort of a step between base compute engine and fully managed app engine, where you're in much more control of your environment, but we help you keep everything alive. And that's actually exactly where Google wants to be. We want you guys to be building cool stuff and basically assembling cool stuff out of all the amazing building blocks that are there. But we want to be your Linux geeks as a service that help keep it alive. Like we don't want you to think about how do we make it perform, how do we keep it alive. Is that a good enough answer for what our plans are, or did you have something else in mind? Okay, good.
How do you guys monitor all these containers? If Kubernetes spins up new containers everywhere,
Yeah.
how do you monitor when you have to?
Us internally for our internal version, or on your when you use it? You mean?
When I use it.
So when you use it, all of your nodes are compute engine instances inside your project. So it's pretty clear that they belong to. It's pretty clear.
What's the CPU and memory usage?
Yeah. So you'll define first probably you'll define what the instance size is that you want to run them on. And then you'll define what Docker instances. So Kubernetes is responsible, for instance, for monitoring where these containers and are they in the right places. You define compute engine, what size compute engine instances, and we take care of that. I could go into my control panel, and we could probably go look at the details. I could see the details in here. Let's see if I can, maybe I should go. But yeah, so I think are you asking the question from a Kubernetes side or a?
I know when I have to scale new containers up, so I have to say that. Well,
Okay. So what we have an autoscaler that you can set up in Compute Engine. Kubernetes also has some autoscaling logic that you can turn on. I think right now the autoscaling logic generally applies to pods rather than nodes. So if you want, you need to kind of be aware it's time to add new nodes, but you can set up the compute engine autoscaler to monitor your nodes. But this is something we work on a little bit because people originally think, oh, can Google give us autoscaling in Kubernetes? And we could, but you're paying us for the Kubernetes resources. And then you might say, you're doing a terrible job of scheduling my containers, you're leaving unused space, you're giving me more because you just want the money from the extra machines, and so you might be mad at us. I think what I've heard about is the roadmap is we should provide an autoscaler node. Actually, all of these components in here are just additional pods. We should provide a base autoscaler pod that can do autoscaling for you on some basic logic and let you replace it with your own autoscaling pod or your own autoscaling logic. It's kind of the roadmap I've heard. But to be honest, I think this is something that's changing so fast. I really am not quite up to date on how we do autoscaling in Kubernetes. Sorry. But so I can look at for instance, I can see the instances that are running my nodes. So here's my Kubernetes master, which is watching everything. Here are the 3 nodes. Oh, I even have an autoscaler set up for it. No, I think that's something I built in another project and forgot to turn off. We can even go into Container Engine and monitor details of the cluster internally, so we can see, okay, on node 1, what's running on node 1. So all of this stuff is monitorable, and then, yeah. So, I mean, it is, so Kubernetes itself is not yet 1.0. There's a lot of stuff on the roadmap before Kubernetes goes to 1.0. And so Container Engine is also not fully, fully generally available. You can use it. I have customers that have launched production workloads on Google Container Engine. That's an alpha service, really? Okay, but they've done it. They were confident that it was doing what they needed. Unfortunately I can't answer the auto-scaling because I haven't tried it myself. Yeah.
Well, I was interested about this actually.
Oh, this sort of thing, yeah. Okay.
I have a question.
Yeah.
So how it solves thing we started with when you said you don't use 1 gigabyte of RAM and you plan not in a perfect shape. So how it solves this issue?
Oh yeah.
It somehow combines and tries to take the most from the machine or from one node. Or
You mean like if you have a Docker image? Oh, right. When you have leftover space
yes,
internally.
Space.
Leftover, any dimension. I think you can never solve that problem perfectly. But the idea of Kubernetes is that it's handling the logic of trying to fit things as well as you
so
can.
it tries somehow to fit the best.
It's good. And actually that logic, that scheduling logic is probably also a node or a pod that you can replace with your own logic if you want. But because one thing I've learned from talking to the Kubernetes team is pretty much everything in there is a piece of logic that you can replace with another, with something else. But I wonder if that sort of thing is in the, that sort of thing should be findable if you dig into the Kubernetes code about how it's scheduled.
Sure.
Well, I mean, not even Google it. Look into the code and go, how do they schedule? Is there a scheduler? Where would it be? How do they? Okay. Yeah, but
I'll Google.
yeah, Google, or just dig through the source code. One last question. Yeah.
When is 1.0?
When is 1.0? 1.0 is when this roadmap 1.0 for Kubernetes is when this roadmap is ready. And I haven't seen any estimations on it because it's not just Google effort, it's a community effort, even though we're kind of the maintainers of it. I don't know. I didn't.
Wouldn't pace?
3 months? 3 months? So you bump into really things that you think should be easy, but aren't when you're doing this. Like scaling up turns out to be fairly easy. We add another node, we add another pod, scaling down turns out to be a little bit of a challenge because you say, okay, first we need to drain all the connections from that. Then we need to make sure it's done. Now, are we confident that everything in that pod is done? We kill it. Are we confident that everything is off that node and nothing new has been scheduled to it? Now we can kill it. So it's much more, actually turns out to be more complicated, for instance, to scale down than it is to scale up. And that's just one example of why it sometimes takes a little longer than you expect to go 1.0. But maybe 3 months? It's been moving super, super fast. So contribute code, make it come faster. So.
Those guys are wrong time zone for me.
Sorry? I don't think you need to worry about time zones these days. Actually, the Warsaw, we've got a teams in Warsaw. Somebody's coming to go to Amsterdam from the Warsaw office, and he's one of the Kubernetes engineers. So maybe they're not the wrong time zone. So I would say go try it, whether you try out the container engine using that GitHub repository or the getting started on container engine, or whether you want to run it at home or somewhere else. You can do that from the regular Kubernetes. You don't have to use our hosted version. Have fun with it, give feedback, or add code. So thanks, guys.
Okay.
Sorry, 10 minutes over.
It's no problem.